So my name is William Isaac. As Julia just pointed out, I'm a PhD candidate at Michigan State University, and I'm presenting the work that I did with my colleague Christian Lum at the Human Rights Data Analytics Group. And our study looked at the role of bias training data and its impact on predictive policing algorithms. So, sorry.
Yeah.
Sorry. I'm not used to talking with microphones. I'm used to just kind of walking around and yelling. So,
You could take it out and hold it.
oh, no, it's all right. I don't want to be an MC. So, I guess for those who are unfamiliar, when we talk about algorithms, we're talking about a process where we're applying some statistical process, be that a regression equation or whatever, and some data to actually leverage these models to give us new insight. And I think that's important because a lot of times what gets lost in the discussion is, we talk about like the formula, but not actually about the data being used. And I think Jeremy just pointed out that this is a question that I think is particularly salient when we talk about predictive policing. But so why does that matter? It matters because when you think about predictive policing, we're looking at what people in the media and more broadly consider crime. But as we pointed out earlier, that we're not actually looking at crime, we're looking at observed police records. And I think when you actually take a step back, that's an important distinction to make because we actually know that there are differences in what crime gets recorded and what crime does get reported. And so that actually matters for what we're actually predicting. And so, because as you actually throw this into an algorithm, you're not predicting future crime. What you're actually predicting is future recorded crimes. Now, in theory, right, if you had all of the data available to you and you had all of crime, you might be able to predict actual crime. But if there are biases that are systematic, if they're random, then perhaps maybe you get a little closer. But if there's systematic biases in the recording of crime, right, that can actually lead to biased predictions. And those biased predictions, when you actually use models that are forecasting in the future using those observed bias data, that let's say you send the police out, they go and patrol a neighborhood, they they go and add new complaints, that data gets added back in. It reinforces the initial bias predictions and actually can amplify, in some cases, the targeting of certain communities in future forecasting. And so as an example, we looked at drug crimes in the city of Oakland, and I accidentally put arrest here, but this is actually incidence data rather than arrest data. So yes, making that important distinction. And so as you can see, right, in a perfect world, you would have a lot more geographic variation in these arrests. But if you notice, there's particular, my laser pointer is not working, but you can see that there are clusters of these arrests, and greater intensity of red indicates more incidents of crime for drug-related offenses. And you can see that the clusters around West Oakland, the Fruitville neighborhood, and down what is known as International Boulevard. And these are predominantly non-white communities in the city of Oakland. Now, what we struggled with was how do you actually get a way of looking at all crime or some sort of representation of all crime? And what we decided to do was actually use a combination of survey data from SAMHSA, which is a health organization at the federal level, and the US Census data to create estimates of where we expect illicit drug users to be. And as you can see, we see a lot more geographic variation in where we expect drug users to be relative to where we actually find drug incidents recorded in police data. And so in theory, if the algorithm did not mimic this bias that we see in the recorded data, then you would be able to see hotspots in other places outside of the areas that they already recorded. So we decided we wanted to test this because we were interested. And so what we did is we used the algorithm that was published in a paper by George Moeller and his co-authors that, for those who maybe are interested in, this is like a self-exciting point model. So this is one of many algorithms that are used for mapping predictive policing. And so what we did is we used this model to actually take a training set of observed crimes for the city of Oakland and forecast in the future and see where they go. And so we have a cool little video here that will show you what happens. So the little blinking dots are actually where the observed crimes are occurring. And we turn on the Predictive algorithm, and as you can see, I guess it's a little hard to see, the red dots are actually where the algorithm is sending the additional police units. And as you can see, you don't see very much variation in the location of the targeted police, and they stay relatively stationary throughout the entire survey, the entire study period. And if you look at the bottom right, we actually targeted what populations are being targeted based on the racial demographic of that each individual grid square that we mapped out. And as you can see, neighborhoods that have a majority of white residents tend to see far less actual targeted policing relative to non-white neighborhoods. And so I will click the next slide, but the video will loop back and forth if you didn't get a chance to see it. So to summarize what you saw in the video, this is actually the summary of where they actually targeted. And if you think back and you look at the actual patterns that you saw in the recorded data, you actually see it's very similar to what Predictive, the algorithm, the self-exciting point model, actually showed in the recorded data. So, really, you're not getting that much leverage from the algorithm itself. It's basically telling you to go back exactly where the recorded observations were originally. Right? There's no variation in these other neighborhoods where, hypothetically, there are actually potential illicit drug users, but they're actually not showing up in the recorded data. And so what we decided to do is take it one step further, because the example that we showed actually didn't include a possibility that when you dispatch police, that you might actually find additional incidents of crime when you're sent out to patrol these neighborhoods. And so what we did is we actually included an additional simulation where we decided, okay, well, what if we added an additional chance that when you send police out, that they're going to find additional units of crime? What would that do to the performance of the algorithm? And what we actually show is that when you do that, actually the targeting becomes even more biased because of the feedback loop that's generated by submitting more incidents of crime into the same areas that were initially recorded in the police data. And so, and in fact, it actually basically doubles. So this graph here, the y-axis is the odds of actually going after a targeted neighborhood, being in a targeted neighborhood, and the x-axis is across time. And as you can see, it starts off roughly at the same place, but about doubles by the end of the survey, the study period. And so, in short, crime is everywhere, but the actual recorded crime is not. And in a perfect world, algorithms could help adjust for this, but the ones that we've seen actually reinforce the bias and can actually amplify it depending on how police allocate their resources and what decisions they make on the ground. And so I think this is important for is my time up?
Yeah.
Okay, well, my time's up based on but I'm happy to talk about it in the questions. Thank you.
Thank you.